Welcome to this coding walkthrough. Today, we will explore problem number 1589, titled Maximum Sum Obtained of Any Permutation. In this session, we'll dive into the problem statement, discuss various approaches, and analyze their complexities. Let's jump right in and start solving. In this problem, you are tasked with maximizing a score by rearranging the elements of an array. You are given an array called nums, which can be reordered in any way, and a list of requests, where each request specifies a subarray of nums using a start and end index. The score is calculated based on these requests. For each request, you take the sum of the subarray specified by the start and end indices, and then add these sums across all requests to get the total score. Your goal is to find the maximum possible score among all permutations of nums. Since the result might be very large, you will return the score modulo 10 to the power of 9 plus 7. The input constraints make this problem challenging, as both the length of nums and the number of requests can go up to 10 to the power of 5. This means we need an efficient solution to handle these potentially large inputs. To better understand the problem, let's look at an example. Suppose nums is 1, 2, 3, 4, 5, and the requests are 1, 3, 0, 1. In this case, you can rearrange nums to maximize the score. One optimal arrangement is 5, 4, 3, 2, 1. For the first request, 1, 3, the subarray becomes 4, 3, 2, and its sum is 9. For the second request, 0, 1, the subarray is 5, 4, and its sum is 9. Adding these two results together gives a total score of 19. This demonstrates how rearranging nums strategically can lead to the maximum possible score. Now, let's examine another example. Consider nums as 1, 2, 3, 4, and the request says 0, 2, 1, 3. An optimal arrangement of nums is 4, 3, 2, 1. For the request 0, 2, the subarray is 4, 3, 2, and the sum is 9. For the request 1, 3, the subarray becomes 3, 2, 1, and its sum is 6. Adding these together gives a total score of 15. These examples highlight the importance of optimizing the order of nums to maximize the contributions of the most frequently requested indices. Finally, there are some important constraints and edge cases to consider. The answer must always be returned modulo 10 to the power of 9 plus 7. For edge cases, if nums has only one element and the request targets that single index, the result is simply the value of that element. For large inputs, where both nums and requests have sizes up to 10 to the power of 5, the solution must be highly efficient to avoid timeouts. You should also account for different request patterns. If the requests do not overlap, each can be handled independently. However, if all requests overlap completely, the optimal solution is to sort nums in descending order. These considerations will guide you in designing a solution that is both correct and efficient. To begin, let's consider the brute force approach. The intuition here is straightforward. We try every possible permutation of the array nums, calculate the sum for each permutation based on the given requests, and identify the maximum sum among them. The steps are simple. First, generate all permutations of nums. Then for each permutation, you iterate through the list of requests. Each request specifies a subarray, so you calculate the sum for that subarray and keep track of the overall maximum sum. However, this approach becomes impractical very quickly. With n permutations to consider, and for each permutation iterating over m requests, the time complexity balloons to O(n). *m*(n). The space requirement is also significant, as we need to store permutations. This exponential growth makes the brute force approach computationally infeasible for larger input sizes, which is why it's not a viable solution for this problem. Now, let's explore the optimized approach using frequency counting. The key observation here is that the contribution of each element in nums to the total sum depends on how frequently its index is included in the ranges specified by the requests. This insight allows us to avoid generating permutations entirely. Instead, we calculate the frequency of each index being included in the requests. The steps are as follows. First, initialize a frequency array frequency with zeros. For each request, increment the frequency at the starting index and decrement it just after the ending index. Then compute the prefix sum of this array to determine how often each index is included. Once that's done, sort nums in descending order and do the same for the frequency array. By pairing the largest values in nums with the highest frequencies, we maximize the sum. This approach is efficient, with a time complexity of O, n plus m plus n log n, which includes building the frequency array, sorting, and calculating the result. The space requirement is linear, making this method far more scalable and practical. The core insight that drives this approach is realizing that the order of elements in nums doesn't matter directly. What truly matters is how often each index in nums is used, as dictated by the requests. Sorting nums and aligning its largest values with the highest frequencies ensures that the contribution to the sum is maximized. The prefix sum technique is another crucial piece, as it allows us to calculate the frequency of each index efficiently without explicitly iterating over all requests. When comparing the two approaches, the brute force method, while conceptually simple, is computationally prohibitive and scales poorly. On the other hand, the optimized approach is efficient, avoids unnecessary calculations, and is scalable. However, it does require a solid understanding of prefix sums, which might be less intuitive for beginners. The chosen strategy is the optimized approach using frequency counting. This method is not only efficient with a time complexity of O, n log n, but it also scales well for larger inputs. By leveraging sorting and prefix sums, we ensure that the largest values in nums are paired with the most frequently used indices, maximizing the sum without the need for explicit permutations or subarray iterations. This balance of efficiency and practicality makes it the most suitable solution for the problem. To solve the problem of maximizing the sum of subarray elements based on given requests, we need a clear strategy. Each request specifies a range within the array, and the goal is to maximize the weighted sum of the array elements. The key insight here is that the most frequently requested indices should be assigned the largest values in the array after sorting. By doing so, we ensure that the highest weights are given to the most important indices, maximizing the total sum. So, the challenge boils down to determining how often each index is covered by the requests and then mapping the values in the array to these frequencies in an optimal way. Now, to implement this, the first step is to compute the frequency of each index in the array based on the requests. We initialize a frequent array of the same size as nums and set all elements to 0. For each request, we increment the starting index in frequency to mark the beginning of the range and decrement the index immediately after the end of the range, if it's within bounds, to mark the end of the range. This is a difference array technique that allows us to efficiently calculate the frequency of each index using a prefix sum. Once we have the frequency for all indices, we sort the frequent array in descending order, ensuring that the most frequently used indices appear first. Similarly, we sort the nums array in descending order so we can pair the largest numbers with the highest frequencies. Once sorted, we multiply each number by its corresponding frequency and sum these products. Finally, the result is returned modulo 10 to the power of 9 plus 7 to handle large numbers and prevent overflow. The solution hinges on a few key insights. First, using a frequency array with a difference array technique significantly optimizes the process of determining how often each index is covered. Instead of iterating through all requests for every index, we reduce the complexity to a combination of difference array updates and a single prefix sum calculation. Second, sorting both nums and frequency ensures that the largest numbers are matched with the most frequently used indices, which is critical for maximizing the weighted sum. Finally, applying the modulo constraint ensures the result remains within standard integer limits, as the weighted sum can grow very large. The primary data structures involved include the frequency array, which tracks the coverage of each index efficiently, and the sorted arrays that guarantee the optimal pairing. Together, these components reduce the problem's complexity and make the solution scalable. Analyzing the complexity of this approach, the time complexity involves three main steps. First, calculating the frequency array using difference array updates and a prefix sum is O, n plus m, where n is the size of nums and m is the number of requests. Second, sorting the nums and frequency arrays takes O, n log n. Finally, computing the weighted sum of the products is O, n. Combining these, the total time complexity is O, n log n plus m. For space complexity, the additional space required is primarily for the frequent array, which is O, n. Thus, the overall space complexity is O(n). This makes the solution efficient and well suited for larger inputs. This Python implementation efficiently solves the LeetCode problem maximum sum obtained of any permutation using a greedy approach combined with prefix sums. Here's a breakdown of the solution. 1. Initialization. We initialize a frequent array to track how many times each index in nums is covered by the ranges in requests. The length of frequency is n+1 to handle boundary conditions. 2. Frequency calculation. For each range, start, end, in requests, we increment frequency, start, indicating the start of coverage, and decrement frequency, n+1, to signal the end of coverage. This step ensures we can calculate the frequency of each index using a prefix sum later. 3. Prefix sum. Using Python's accumulate function from iter tools, we compute the prefix sum of the frequent array. This gives the actual frequency of each index in nums based on the overlapping ranges in requests. For sorting, to maximize the sum, we sort both the nums array and the frequent array in descending order. By pairing the largest numbers in nums with the highest frequencies in frequency, we ensure the maximum contribution to the sum. 5. Calculate maximum sum. We iterate over the sorted nums and frequency arrays, multiplying corresponding elements to compute the weighted sum. The result is taken modulo 10⁻9 plus 7 to handle large numbers, as required by the problem constraints. 6. Return result. Finally, the computed maximum sum is returned as the result. This solution is efficient, with a time complexity of O(n) log n plus m, where n is the length of nums and m is the number of requests. Sorting the nums and frequency arrays dominates the runtime, making this approach optimal for the given constraints. Here, we begin by defining a method called maxSumRangeQuery, which takes an array of integers, nums, and a 2D array, requests, as inputs. The goal is to determine the maximum sum we can obtain by permuting the elements of nums based on the frequency of their usage in the given requests. First, we initialize an array, frequency, which will help us track the frequency of each index in nums. This array has a size of n+1 to handle boundary conditions when working with ranges. Next, using a loop, we iterate over each request in the requests array. For each request, we increment the frequency at the start index and decrement it at the index immediately after the end. This ensures that when we later compute the prefix sum, we can determine the correct frequency for each index. After processing all requests, we convert the frequency array to a prefix sum array, where each index in frequency reflects the total frequency of the corresponding index in nums. This step is crucial because it consolidates the range updates into usable frequency values. Finally, we sort the nums array in ascending order and sort the relevant portion of the frequent array, which is the first n elements, in ascending order as well. This prepares us to calculate the maximum sum in the next step. Now that both nums and frequency arrays are sorted, we can calculate the maximum sum. We initialize a variable, maxSum, to 0, and a constant, mod, to handle large numbers and ensure the result fits within the constraints of the problem. Using a for loop, we iterate through the first n elements of nums and frequency. At each step, we multiply the corresponding elements of nums and frequency, add the result to maxSum, and take the modulo with mod to prevent overflow. This multiplication ensures that the highest values in nums are paired with the highest frequencies in frequency, maximizing our sum. After completing the loop, the maxSum variable contains the maximum sum modulo 1,000,007. Finally, we return maxSum as an integer, completing the implementation. This approach ensures optimal performance by leveraging sorting and prefix sums, making it efficient even for larger inputs. Here, we are solving the problem using an example where nums is 1, 2, 3, 4, 5, and requests are 1, 3, 0, 1. The first step is to calculate the frequency of each index. We begin by initializing a frequency array of size n+1, filled with zeros, frequency equals 0, 0, 0, 0, 0, 0. For the first request, which is 1, 3, we increment frequency 1 by 1 and decrement frequent 4 by 1. This updates the array to 0, 1, 0, 0, -1, 0. Next, for the second request 0, 1, we increment frequency 0 by 1 and decrement frequent 2 by 1, resulting in frequency equals 1, 1, -1, 0, -1, 0. To prepare for the next step, we convert this array into a prefix sum. Using accumulation, the prefix sum gives us 1, 2, 1, 1, 0, 0, and we drop the last element, leaving frequency equals 1, 2, 1, 1, 0. Finally, we sort both nums and frequency in descending order. Nums becomes 5, 4, 3, 2, 1, and frequency becomes 2, 1, 1, 1, 0. This sets us up to calculate the maximum sum. With nums and frequency sorted, we calculate the maximum sum using the formula nums I asterisk frequency I % mod. We initialize max_sum as 0 and begin multiplying corresponding elements of nums and frequency. The first product is 5 multiplied by 2, which equals 10. Adding this to max_sum gives 10. Next, we multiply 4 by 1, resulting in 4, and adding it to max_sum gives 14. Then, 3 multiplied by 1 gives 3, updating max_sum to 17. Multiplying 2 by 1 yields 2, making max_sum 19. Finally, 1 multiplied by 0 gives 0, so max_sum remains 19. The maximum sum for this example is therefore 19. Now, let's look at a second example where nums is 7, 3, 9, 4, and requests are 0, 2, 1, 3. Just as before, we start by calculating the frequency of each index. We initialize frequency equals 0, 0, 0, 0, 0. For the first request, 0, 2, we increment frequency 0 by 1 and decrement frequency 3 by 1, resulting in frequency equals 1, 0, 0, minus 1, 0. For the second request, 1, 3, we increment frequency 1 by 1 and decrement frequent 4 by 1, updating frequent to 1, 1, 0, minus 1, minus 1. Next, we compute the prefix sum of this array. After accumulation, frequency becomes 1, 2, 2, 1, 0, and we drop the last element, leaving frequency equals 1, 2, 2, 1. Sorting nums in descending order gives 9, 7, 4, 3, and sorting frequent in descending order gives 2, 2, 1, 1. To calculate the maximum sum for this example, we again use the formula nums I asterisk frequency I % mod. We initialize max_sum as 0 and start with the first product, 9 multiplied by 2, which equals 18. Adding this to max_sum gives 18. Next, we multiply 7 by 2, resulting in 14, updating max_sum to 32. Then, 4 multiplied by 1 gives 4, making max_sum 36. Finally, 3 multiplied by 1 yields 3, bringing max_sum to 39. Thus, for this example, the maximum sum is 39. For this third example, we have nums equals 10, 20, 30, and a single request, 0, 2. The first step is to calculate the frequency of each index. We initialize frequency equals 0, 0, 0, 0. For the request 0, 2, we increment frequency 0 by 1 and decrement frequency 3 by 1. This updates frequency to 1, 0, 0, minus 1. Then, we compute the prefix sum of this array. After accumulation, frequency becomes 1, 1, 1, 0, and we drop the last element, leaving frequency equals 1, 1, 1. Sorting nums in descending order gives 30, 20, 10, and since frequency is already sorted in descending order, it remains 1, 1, 1. Finally, we calculate the maximum sum using the formula nums I asterisk frequency I % mod. Starting with max_sum as 0, we compute the first product, 30 multiplied by 1, which equals 30. Adding this to max_sum gives 30. Next, we multiply 20 by 1, which results in 20, updating max_sum to 50. Lastly, we multiply 10 by 1, yielding 10, making max_sum 60. Therefore, the maximum sum for this example is 60. To analyze the time complexity of our solution, we start by breaking it into its individual components. First, the initialization of the frequency array takes n time since we create an array of size n plus 1 and fill it with zeros. Next, we process the requests. For each of the m requests, we increment the start index and decrement the n plus 1 index of the frequency array, which takes m time overall. After processing these requests, we calculate the prefix sum of the frequency array. This operation requires a single pass through the array, resulting in an O(n) time complexity. Finally, we need to sort both the nums array and the frequent array in descending order. Sorting each array independently requires O(n log n) time, making it the most computationally expensive step of the solution so far. Once the arrays are sorted, we compute the maximum sum by iterating through the nums and frequency arrays. During this step, we multiply corresponding elements from the two arrays, apply the modulo operation for each result, and accumulate the total. This computation involves a single loop over the arrays, which takes O(n) time. Now, combining all the steps together, we get O(n) for initializing the frequency array, O(m) for processing the requests, O(n) for computing the prefix sum, O(n log n) for sorting, and O(n) for calculating the sum. Among these, the sorting step dominates the overall time complexity, making the final time complexity O(m plus n log n). This ensures that our solution remains efficient even for larger input sizes. Now let's analyze the space complexity of the solution. The primary contributor is the frequency array, which has n plus 1 elements and therefore requires O(n) space. Additionally, the accumulate function used for prefix sum calculation creates an intermediate array of the same size, adding another O(n) to the space requirement. Sorting, on the other hand, is performed in place for both the nums and frequency arrays. This means no additional space is allocated during sorting beyond the input itself, so the sorting step uses O(1) space. Finally, the algorithm uses a few scalar variables such as mod and max_sum, which require constant space, or O(1). Combining these factors, the total space complexity is determined by the frequency array and the intermediate array created during accumulation, resulting in a final space complexity of O(n). When we analyze the best, average, and worst cases for this algorithm, we observe that the time complexity remains consistent across all scenarios. Regardless of the input, the solution always requires sorting the nums and frequency arrays and calculating the prefix sum of the frequency array. These operations are necessary for every input and contribute to the dominant O(n log n) term. Thus, the time complexity does not vary based on the properties of the input, making the best, average, and worst cases all equal to O(m plus n log n). This consistency ensures predictable performance for the algorithm across different types of inputs. Let's compare this optimized approach to a brute force solution. In the naive method, we would iterate over all m requests and, for each request, manually sum the contributions of the interval for all indices in nums. Since processing each request takes O(n) time, the total time complexity of the brute force approach becomes O(m*n). This is significantly worse than the optimized solution, especially when both m and n are large. The optimized solution, on the other hand, uses a frequency array combined with prefix sum computation to efficiently calculate contributions for all indices. By sorting the arrays, it ensures that the largest values in nums are paired with the highest frequencies. These improvements reduce the time complexity to O(m plus n log n). The mathematical reasoning behind this complexity is that sorting, with its O(n log n) time, dominates the overall performance, while the other steps, such as frequency updates and prefix sum calculation, are linear in nature. This makes the optimized solution far more scalable and efficient for larger problem sizes. When tackling this problem, there are a few common mistakes to be aware of. First, overcomplicating the brute force approach can often trip up beginners. The purpose of brute force is to provide clarity and a foundation for understanding the problem, not efficiency. By overthinking or prematurely optimizing the implementation, you risk creating convoluted code that is harder to debug and more prone to logical errors. Another frequent issue is ignoring constraints. The problem's constraints, like the size of the nums array or the range of requests, are crucial for designing an efficient solution. Neglecting them can lead to algorithms that exceed time limits or make incorrect assumptions about the input. Finally, incorrect usage of prefix sums is another pitfall. Many errors stem from improper index adjustments, such as mixing up inclusive and exclusive ranges. These off-by-one errors can lead to incorrect sums, jeopardizing the entire solution even if the overall logic is sound. Another key consideration is the importance of sorting the requests in certain approaches. Skipping this step can lead to suboptimal solutions because sorting ensures that the largest numbers in the input array align with the most frequently requested ranges, maximizing the sum. Neglecting this can significantly impact the efficiency of your solution. Additionally, overlooking edge cases is a common mistake. Examples include scenarios where the input array is empty or when a request covers the entire range of the array. Failing to address these can result in runtime errors or incorrect results. Properly handling edge cases not only makes your code robust but also saves time during debugging, particularly in high-pressure interview settings. From an interview perspective, there are several strategies you should keep in mind. Start by optimizing incrementally. Even if your initial solution is inefficient, it's important to demonstrate your understanding by walking through a brute force approach. Afterward, you can discuss ways to optimize, such as reducing redundant computations or leveraging sorting and greedy techniques. Communicating your thought process is equally important. For instance, explain why sorting the frequency array helps in maximizing the sum. This shows clarity and intentionality in your approach. Additionally, consider space-time trade-offs. Using structures like frequency arrays or prefix sums can significantly reduce redundant calculations, even if they require extra space. Lastly, testing your solution on small examples during the interview is a great way to validate your logic and showcase your thoroughness. It reflects a methodical approach and helps catch potential issues before scaling up. This problem shares similarities with several others that you might encounter on LeetCode, which can help solidify your understanding of related concepts. For example, LeetCode 1090, Largest Values from Labels, focuses on maximizing a score under specific constraints, which aligns well with the greedy strategies discussed here. Another related problem is LeetCode 1834, Maximum Element After Decreasing in Rearranging, which also employs a greedy approach to achieve an optimal sum. LeetCode 560, Subarray Sum equals k, centers around prefix sums, a pivotal concept for this problem as well. Finally, LeetCode 253, Meeting Rooms 2, is a range-based problem that benefits from sorting and frequency tracking, much like the techniques used to solve this permutation problem. Exploring these problems can deepen your understanding of the underlying patterns and strategies. There are several alternative approaches to solving this problem, each with its own trade-offs. One common method is using a prefix sum array combined with sorting. Here, you count the frequency of each index using the prefix sum technique, then sort both the frequency array and the input array nums. By multiplying the largest numbers with the highest frequencies, you can achieve the maximum sum efficiently in n log n time. However, this approach does require additional space to track frequencies. Another option is using a segment tree or a range query structure. This allows you to dynamically compute sums based on the requests, making it more adaptable to changes in input. The trade-off here is that this method is more complex to implement. Lastly, a pure greedy approach focuses on pairing the largest numbers with the most frequently accessed ranges, without explicitly calculating all permutations. While this is simpler and faster, it requires careful sorting and mapping logic to ensure correctness. Each approach has its pros and cons, and the best choice depends on the specific constraints and requirements of the problem. To wrap up, we covered problem number 1589 and examined multiple approaches to solve it efficiently. We discussed key insights and takeaways that can strengthen your problem-solving skills. Thank you for watching. Be sure to like, subscribe, and join me for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!